Welcome viewers. Today we'll see the electric field intensity followed by the electric field intensity due to finite charged wire. First we'll see the definition of electric field intensity. The electric field intensity is nothing but force per unit charge F divided by Q. That is, the electric field intensity at a point is defined as the force per unit charge on a test charge being as small as possible in comparison with the other charges forming the system. So the general formula for the electric field intensity is F divided by Q. We can refer this diagram. We have one charge is available placed at the origin, capital Q, and another charge, small q, placed at a distance r meter from the origin at point A. This UR is the unit vector. So we have one force, one charge at origin, another charge at a distance r meter at a point A. So due to these two charges, the force will be created. That force is given by, based on the Coulombs law. The force is given by Q into capital Q into small q divided by 4 pi epsilon r square. That r is nothing but distance between the charges. So bring this q in the denominator, so that we got q divided by 4 pi epsilon r square. So this F by Q is nothing but electric field intensity. So that is E equal to Q divided by 4 pi epsilon r square. So this is the general formula, electric field intensity, Q divided by 4 pi epsilon r square, right? So in this derivation, we are going to start with this basic equation, E equal to Q divided by 4 pi epsilon r square. Before starting the derivation, we will see the charge distribution. What are the charge distributions are available? So there are three type of charges available. Charge density, linear charge density, lambda dq by dl, that is divided by length. Then it is called as a linear or line charge density by considering only the line. The unit is coulomb per meter, right? If we consider the area, then it is called a surface charge density, sigma dq divided by ds. Here we are considering the surface area, coulomb per meter square. If we consider the volume, then it is called a volume charge density, rho dq divided by dv, coulomb per meter cube, right? So in the density, we have three types available. Linear density means length, surface charge density means area, volume charge density means volume, right? So we have lambda, sigma and rho. Based on that, we have the derivation. Now we'll see the electric field intensity due to a finite charged wire. One finite charged wire is there. In that, we are going to obtain the expression for what is the electric field intensity, right? You can refer this diagram. So this is a finite charged wire, AB. Finite charged wire, it is termed as AB. So this is the point P. At this point only we are going to find the electric field intensity due to this charged wire, right? So the distance between this point P and the midpoint or origin is d meters, right? This finite charged wire is assumed with a lot of charges. Point charges are available. N number of point charges are available in the finite charged wire. In that we assumed only one charge, right? So that the details available here. Lambda equal to dq by dl. Because of length, there is a finite charged wire, we are assuming the linear charge density dq by dl, lambda. From that we can find here the L is replaced by x. Due to the x, we are considering x, so that dq divided by dx, that is, to cross multiply this, dq equal to lambda into dx. So the small charge available at this point is represented as lambda into dx, that is linear charge density into small distance dx. Like that, there are n number of charges available. For the calculation purpose, we consider only one charge at a distance x meter, that can be represented as lambda into dx. So the distance between this point charge and point P is r meter, right? So this triangle is drawn separately here for calculation purpose, and dxr is drawn separately. This is the theta, angle theta. For calculation purpose it is drawn separately. So this is the theta, this angle will be 90, means automatically this remaining angle will be 90 minus theta, right? So due to the point charge, we have the electric field intensity is produced on the opposite side, dE. For any point, if it is inclined, the total electric field intensity will be divided into horizontal component and vertical component, DEH and DEB. If any point is there, that will be resolved into horizontal and vertical component, right? So this angle is 90 minus theta, mean automatically this angle will be 90 minus theta, right? So this triangle, in order to find the horizontal and vertical component, this triangle is drawn separately here, right? So this is the horizontal component, this one. This will be total component, this one. This will be vertical component, DEH, DEB and DE. And the angle will be 90 minus theta. So from this we can find the what is the expression for horizontal component and what is the expression for vertical component. How will you find? You find the expression for cos 90 minus theta. Cos 90 minus theta means adjacent side by hypotenuse. What is adjacent side? DEH divided by DE. Cos 90 minus theta is nothing but adjacent side by hypotenuse. Adjacent side is DEH, hypotenuse is DE. You cross multiply this, so that DEH equal to DE cos 90 minus theta. So you can simply remember horizontal component equal to total component multiplied by cos of theta, right? For anywhere we can use that. The horizontal component equal to total component multiplied by cos of theta. Similarly, we can find sin 90 minus theta. Sin theta means, sin 90 minus theta means opposite side by hypotenuse. Opposite side is DEV, hypotenuse DE. So DEV by DE equals is given by sin 90 minus theta. You cross multiply this, so that DEV equal to DE sin 90 minus theta. So vertical component equal to total component multiplied by sin 90 minus theta, right? Now we got the expression for horizontal component as well as vertical component. From that we can find the total component also, right? So in this diagram, this for point A, the wire is named as AB. The equivalent angle will be alpha for A. For B, equivalent angle will be beta, right? During the limit, while substituting the limit, we can refer this angle alpha and beta equivalent to A and B, right? So that description is given here. The wire is uniformly charged with a charge density lambda coulomb per meter. The wire is assumed to be formed by several point charges. In that we consider only one point charge at a distance x meter, right? So the dE is the small electric field intensity due to the small charge. R is the distance between the charge dq and point P, right? The detail about the diagram is given. Now we'll see the electric field intensity, right? The general formula just now we discussed, E equal to Q divided by 4 pi epsilon R square. That is the general formula for electric field intensity, right? We consider the small charge dq, so that the electric field intensity also small, dE. Further we can go for integration. At that time we will get the total electric field intensity, so that E become dE, Q become dq divided by 4 pi epsilon R square. But dq is given as lambda into dx in terms of linear charge density. So dE equal to lambda dx divided by 4 pi epsilon R square, right? So after substituting these values, right, the lambda we got this value. You take it, this is a equation number 1, right? Now what we are going to do, we are going to find the dx and R value from this triangle, right? Dx and R from this triangle. This triangle already we discussed, right? In this triangle, this is x, d and r, this is the theta. Find the expression for tan theta. Tan theta means what is that? Opposite side by adjacent side, d by x. Opposite side by adjacent side, d by x, right? You exchange this value. So x equal to d by tan theta. 1 divided by tan theta is cot theta, right? So x equal to d cot theta. But here what we need is dx. So differentiate on both the side. Dx equal to differentiation of d cot theta. So differentiation of this d is taken outside. Differentiation of cot theta is minus cosecant square theta d theta. Differentiation of cot theta is minus cosecant square theta into d theta. Therefore dx equal to minus d cosecant square theta into d theta. Right. Similarly, find the sin theta. Sin theta means opposite side by hypotenuse, d divided by r. Opposite side by hypotenuse, d divided by r. Cross multiply this. So r equal to d by sin theta. 1 by sin theta is cosecant theta. So r equal to d cosecant theta. Now we got the expression for dx and r. So these two can be substituted in equation number 1. Right, now substitute this value. This is the equation 1, lambda dx divided by 4 pi epsilon r square. In the lambda into substitute dx. Dx is minus d cosecant square theta into d theta divided by 4 pi epsilon. R is nothing but d cosecant theta. So r square means d square cosecant square theta. So this cosecant square theta got cancelled. 1d got cancelled, right? So the negative symbol is available. So minus lambda d theta, this d theta divided by 4 pi epsilon d. Right, now we got the expression for electric field intensity, small electric field intensity, minus lambda d theta divided by 4 pi epsilon d. We will take this is equation number 2. Right, we already discussed we have horizontal component and vertical component. First we will find the horizontal component. Right, what is horizontal component? Horizontal component equal to total component multiplied by cos 90 minus theta. From the triangle we already got this expression. So cos 90 minus theta can be written as sin theta. Cos 90 minus theta is nothing but sin theta. So deh equal to de sin theta. We got this value de. From equation 2 we have this de value. So we are going to substitute this de value from equation number 2. Right. So that deh equal to minus lambda 4 pi epsilon d, the sin theta is there, sin theta into d theta, right, minus lambda divided by 4 pi epsilon d sin theta d theta. So this is nothing but a small electric field intensity, horizontal component. By integrating on both the side, we will get the total electric field intensity. So we can go for integration. Minus lambda divided by 4 pi epsilon d sin theta d theta. What is the limit for the integration? That is very important. The limit is nothing but we need to consider the entire length of the cable, AB. AB is the length of the cable. But integration is with respect to theta. So that we are taking alpha and beta. Equivalent for point A, the equivalent angle is alpha. Point B, the equivalent angle will be beta. So that we are taking beta to alpha. Right, it is clear. So for length, instead of length we are taking the angle because the integration is with respect to theta. Right, now we'll go the integral deh is nothing but eh minus lambda divided by 4 pi epsilon d is constant. Only we need to integrate sin theta d theta with a limit beta to alpha. Right, so minus lambda divided by 4 pi epsilon d, the integral sin theta is minus cos theta with a limit beta to alpha. You substitute the limit minus cos alpha. While substituting lower limit, one negative will be there, already one negative is there, so it becomes positive cos beta. Right, so you multiply inside this negative so that this become positive, cos alpha minus cos beta. Lambda divided by 4 pi epsilon d cos alpha minus cos beta. So this is the horizontal component. We got the expression for horizontal component. Now we'll see the vertical component. Vertical component is given by dEV equal to dE sin 90 minus theta, sin of theta. Sin 90 minus theta can be written as cos theta. So dEV equal to dE cos theta, right? Now we can substitute the dE value from equation number 2. Equation number 2 we have dE value, so that dEV equal to, this dE is nothing but minus lambda divided by 4 pi epsilon d cos theta into d theta. Right. This is for small value. By integrating on both the side, we will get total vertical component, right? So it is integrated. The limit is beta to alpha. We already discussed the limit will be beta to alpha. So integral dE is nothing but EV. So this will be EV, vertical component, equal to minus lambda divided by 4 pi epsilon d integral beta to alpha cos theta into d theta. These are all constant. Only we need to integrate cos theta, right? So that minus lambda divided by 4 pi epsilon d, this integral cos theta is sin theta. We need to substitute the limit beta to alpha. So minus lambda divided by 4 pi epsilon d, the limit is sin alpha minus sin beta, right? So one more negative is available. While multiplying negative, what we got? Minus sin alpha plus sin beta, right? So finally we can exchange this value, lambda divided by 4 pi epsilon d sin beta minus sin alpha. This will be vertical component. Then the total component, I will get the total component. The resultant electric field intensity is nothing but E equal to square root of vertical component square plus horizontal component square plus vertical component square. E equal to square root of EH square plus EV square, right? So in this video we discuss the electric field intensity, the definition for electric field intensity, then charge distribution, 3 type of charge distribution, then electric field intensity due to a finite wire. We got the expression for horizontal component, vertical component, then finally we got the total component. Welcome viewers. In this video we will see the electric field intensity due to a charged disk. The charged disk is available. In that we are going to see what is the electric field intensity. A disk is with a radius a meter, that is uniformly charged with the charge density sigma coulomb per meter square. That is nothing but surface charge density. So a charged disk is nothing but like a CD, compact disk. The entire surface we are going to consider. So that here we are using the charge density sigma coulomb per meter square, right? By referring this diagram, this is the charged disk with radius a meter. We have the charged disk with radius a meter available. The disk is assumed to be having several rings of increasing radius. Starting from 0, there are n number of rings are available. Starting from 0, the radius of the rings keep on increases and reaches the maximum value of radius a. In this we consider one ring at a distance x meter. The ring is assumed to be having several rings of increasing radius. In that we consider one ring for the calculation purpose at a distance x meter. Our aim is to find the electric field intensity at this point P. The distance between this point P and the center of the disk is d meters. The distance between point P and this small segment is r meter. This will be x meter. So this triangle is drawn separately here, d x r. During the calculation we can refer this triangle. So this is a small segment dx. The angle will be alpha. So when the radius increases, the angle alpha will increase. The radius increases from 0 to a. So in terms of angle, it increases from 0 to alpha. During the limit we need this value alpha, right? So we have the charged disk with radius a. It is assumed to be having several rings. We consider one ring at a distance x meter. The thickness is dx. Our aim is to find the electric field at this point P. which is at a distance d meter from the center of the ring. The distance between this point and point P is r meter. This will be x meter. So this triangle is drawn separately. Because of surface charge density, sigma equal to dq divided by ds. From that, dq equal to sigma into ds. Right. So it is given in terms of surface charge density. So the description is given here. It is required to determine the electric field intensity at point P, which is at a distance d meter from the center of the disk. Right. Our aim is to find the electric field intensity at this point P, which is at a distance d meter from the center of the disk. The disk is assumed to be formed by several rings of increasing radius from 0 to A. They keep on increasing. Several rings are available. In that we consider one ring of radius x meter with a thickness of dx. Right. So due to this small ring, the electric field intensity will be dE due to this small charge dq. The charge is small, so the electric field also small, dE. By integrating, we will get the total electric field intensity. So another important point is the perpendicular field is 0. If we consider any object, perpendicular field, that is vertical component, will be 0. Only the differential x component is available. X component means horizontal component. You know that vertical component, horizontal component, two terms available. Horizontal component equal to total component multiplied by cos of theta. Vertical component equal to total component multiplied by sin of theta. So here vertical component is 0, only we have horizontal component is available. Now we'll start with the electric field intensity. General formula Q divided by 4 pi epsilon r square. Electric field intensity E equal to Q divided by 4 pi epsilon r square. We consider only small charge, so that dE equal to dQ divided by 4 pi epsilon r square. Only the horizontal component available, so that it is multiplied by cos theta. Right. So small electric field, small charge, and this will be horizontal component. So that is nothing but dE equal to this dQ can be replaced by surface charge density sigma into ds. Already this is available in the near the diagram, sigma dot ds divided by 4 pi epsilon r square into cos theta. So finally we have dE equal to sigma ds divided by 4 pi epsilon r square into cos theta. Now we'll see the expression for this ds. But this S is nothing but surface area of the disk. It's like a compact disk. S equal to pi r square. You know that area of the disk will be pi r square. So here we need ds, so differentiate on both the side. So that ds equal to differentiation of pi r square. So ds equal to pi, the differentiation of r square is 2r into dr. Right, so that it is 2 pi r dr. The ds value will be 2 pi r into dr. But in the diagram we consider the x. We consider one small ring at x meter. So that 2 pi x dx. Right, ds equal to 2 pi x dx. Now we can replace this ds with 2 pi x dx. So that value is substituted here. dE equal to sigma, this ds is 2 pi x dx divided by 4 pi epsilon by epsilon r square into cos theta. This 2 pi, here the 2 pi got cancelled. So what we got, sigma x dx divided by 2 epsilon r square into cos theta. We'll take this is equation number 1. So after substituting all the value, we got this expression. Now we have one triangle is available. From this triangle we are going to find the expression for x followed by dx and r. Right, x followed by dx and r we can calculate, we can found from this triangle. So first we will find the tan theta. Tan theta is nothing but opposite side by adjacent side. So this is theta, opposite side is x, adjacent side is d. So x by d. Right. So tan theta equal to x by d, right? So that x equal to tan theta into d. You cross multiply this, so that x equal to d tan theta. Now we got the expression for x equal to d tan theta. We need dx also, so that differentiate on both the side. So dx equal to differentiation of d tan theta. So dx equal to d, differentiation of tan theta is nothing but secant square theta into d theta. So dx will be d secant square theta d theta, right? So we got the expression for x as well as dx. Now we can go with the cos theta. Cos theta equal to adjacent side by hypotenuse. Cos theta equal to adjacent side by hypotenuse. So d divided by r. We cross multiply this, right? You exchange these two values. So r equal to d by cos theta. So that r equal to 1 divided by cos theta is secant theta. So that r equal to d secant theta. Now we got the expression for r also. Now we are going to substitute this x value, dx value and r value, r expression in this equation number 1. Now we'll substitute this value x, dx and r in equation number 1. What is equation number 1? Sigma x dx divided by 2 epsilon r square into cos theta. That is the expression for, that is the equation 1. Now we'll substitute sigma x is nothing but d tan theta, dx is nothing but d secant square theta into d theta. Again this cos theta is available, divided by 2 epsilon r square. R square is d square secant square theta, right? D value, dx value and r value is are substituted. The secant square got cancelled. Here d square is available, here also d available 2 times. So d square also got cancelled. So what we have? Sigma tan theta cos theta d theta divided by 2 epsilon. After cancelling this, we got this value. So this tan theta can be written as sin theta by cos theta. Sigma divided by 2 epsilon. Tan theta is written as sin theta by cos theta into cos theta d theta. So this cos theta got cancelled. So what we got? dE equal to sigma divided by 2 epsilon sin theta d theta. Now we got, after substituting all the value, we got this expression. So this is due to small charge. So by integrating on both the side, we'll get the total electric field intensity, right? Now we'll go for the integration. So integral dE equal to integral sigma divided by 2 epsilon sin theta d theta. What is the limit for this integration? We need to consider entire radius of the disk. Entire radius is a meter. But the integration with respect to theta, so that we are considering the angle alpha, right? So when the radius increases, the alpha also increases. So we are taking the limit 0 to alpha, very equivalent to 0 to a, right? So sigma divided by 2 epsilon is constant, only we have sin theta. Integral sin theta is minus cos theta. We need to substitute the limit 0 and alpha, upper and lower limit. So sigma divided by 2 epsilon, this while substituting the upper limit minus cos alpha plus, so already one minus is there, while substituting lower limit we have one more minus, so it become plus cos theta, cos 0. So sigma divided by 2 epsilon minus cos alpha plus cos 0 value will be 1, right? So while rewriting, the electric field intensity E equal to sigma divided by 2 epsilon 1 minus cos alpha, right? So this is the final expression for electric field intensity due to a charged disk, sigma divided by 2 epsilon 1 minus cos alpha. Now next we'll see the electric field intensity due to charged ring, right? We'll see that. Now followed by the disk, we'll see the charged ring, electric field intensity due to the charged ring. What is this charged ring? Yes, a wire of small cross section is bent in the form of circular ring. One lengthy wire is available two ends are joined together and form the circular ring. So here the wire is available, so that we are using linear charge density, lambda equal to dq by dl, so that dq equal to lambda into dl. Because of because of wire, lengthy wire is there, so that we are using linear charge density. The wire is uniformly charged with the charge density of lambda coulomb per meter. Right, here we are using the linear charge density, so that we are using lambda. Now we'll refer the diagram. So one lengthy wire is available. Now the lengthy wire is joined together. Two ends are joined together and form the charged ring. Right, the radius is a meter. So the length of the wire is nothing but circumference of this ring. Both are equal. Lengthy wire become the ring, so circumference of the ring is equal to length. So our aim is to find the electric field intensity at this point P, which is at a distance h meter from the center of the ring. Here we consider one small segment dl. L is the length, dl means small length. The distance between this segment and point P is r meter. This angle will be alpha. Right, similarly this angle also alpha. So this triangle is drawn separately here, A, R, H, with an angle alpha. From that, if you find cos alpha means adjacent side by hypotenuse, H by R. During the calculation, we can use this cos alpha equal to H by R. So one lengthy wire is available. The two ends of the lengthy wire is joined together and form the circular ring. The radius is A. Our aim is to find the electric field intensity at this point P, which is at a distance h meter from the center of the ring. We consider one small segment dl. The distance between these two is r meter. This triangle is drawn separately with an angle alpha. Now we'll see the description. It is required to determine the electric field intensity at point P, which is at a distance h meter from the center of the ring. Right? We have the point P, which is located at a distance h meter. We consider only small charge, so that the electric field intensity also small, dE. Right? So dE is nothing but electric field intensity due to the point charge dq. So now we'll consider the small length dl. At the small length dl, the charge will be dq. Right? Now we'll go to the derivation. We know that electric field intensity E equal to Q divided by 4 pi epsilon r square. Due to small charge, it becomes dE equal to dq divided by 4 pi epsilon r square. Only horizontal component available, so that cos alpha. Right? So the dq can be replaced by lambda into dl, linear charge density. Right? So lambda dl divided by 4 pi epsilon r square into cos alpha. This lambda L is nothing but the circumference. I already told circumference, that is A into d theta. That is radius as well as theta. So when the circle it is rotates, the theta also varies. So it can be replaced by A d theta, this dl. So this is only the small electric field. By integrating on both the sides, we will get the total electric field. So integral dE equal to integral lambda A cos alpha d theta divided by 4 pi epsilon r square. What is the limit? 0 to 2 pi. That is 360 degree. This d theta vary from 0 to 360 degree rotation circle. Because of ring, it is 360 degree. Right. So in this, lambda A cos alpha divided by 4 pi epsilon r square is constant. Only we have d theta. Right. So the integral d theta is theta. We have to substitute the limit 0 to 2 pi. So while substituting, what will happen? Lambda A cos alpha divided by 4 pi epsilon r square into 2 pi. Lower limit is 0, only 2 pi. This got cancelled. The 2 is there. So that lambda A cos alpha divided by 2 epsilon r square. Already we have the cos alpha value, that is h by r. Near the triangle it is available. So that lambda a h divided by 2 epsilon r cube. Finally we got the expression for electric field intensity due to the charged ring is E equal to lambda a h divided by 2 epsilon r cube. So in this video we got the expression for electric field intensity due to charged disk and charged ring.